Hello everybody, welcome to today's video. Today we will be solving trigonometric equations. So we have a bunch of different types that we're going to look at here. We're going to start by looking at linear trig equations for just sine and cosine to get us started, and then we'll look at equations involving just a single trig function and what we can do from there. We'll look at using our calculator to solve some trig equations. There's some extra thinking to do there since the inverse trig functions on our calculator will only give us back that restricted portion of the unit circle depending on which trig function we're looking at. We'll look at some trig equations in quadratic form and use some substitutions to solve. We'll look at solving some trig equations using some fundamental identities that we already know. And then we'll look at solving some trig equations with multiple angles, meaning like double angle, triple angle, that sort of thing, in order to find all of our solutions there. So let's get into it. We're going to start with this motivating idea here. And it's not an exact correspondence, but it is pretty close to the situation that we're in. But think about these scenarios involving square roots. So if I'm asked to just evaluate the square root of 4 here, what the square root of 4 is saying is find me some number that when you square it gives us 4. And of course we would get 2 there, but it's also technically true that negative 2 squared gives us 4. But we restrict our values here in order to, in this case, ensure a function. For inverse trig functions, we do something similar to ensure that we can get one-to-one functions. But the idea is similar here, that there is only one solution because we are looking at some restricted values here. So for the square root function in general, well, in general, it looks like that because we only take the top functions. Like I said, there's technically negative versions of these numbers as well that would work when you square them. Will give us whatever x is for this function, square root of x. And we just ignore the bottom portion to ensure we have a function. But if I'm asked to solve instead x squared equals negative 4, there are 2 values that do that for us. And typically when we do this, we think about doing plus and minus the square root of 4, which will give us plus and minus 2. So there are 2 solutions here that we have to consider. So depending on the scenario we're in, here, if the square root of 4 or the square root of x is already in our problem, then we're looking at some restricted values. If we're just asked to solve for some x, we're not looking at restricted values anymore. I'm literally just trying to find every value of x that when I plug them in and square it would give me 4. And there are two answers that do that here for us. There's negative 2 and positive 2. So the same logic applies to our trig functions going forward. If we're just asked to evaluate something like cosine inverse of 1/2, this cosine inverse is already in the problem. If we're going to set this equal to theta and think about, okay, cosine of what angle theta would give me 1/2, we're thinking about our restricted domain. So we're thinking about, okay, I'm only looking for values that, or angles that live in the top half of the unit circle here, and so 1/2's about there, and we can figure it out that way. But if I'm asked to instead solve for x, and this is what we're going to start looking at, cosine x equals 1/2, we might think about using inverse trig functions, but the truth is that we are not looking at restrictions anymore. If I think about drawing this unit circle over here, and I'm thinking about the cosine being 1/2, well, now I'm not restricting myself to just the top half of the unit circle. There is still a solution, of course, in the top half of the unit circle, but there's also one in the bottom half of the unit circle that we might not have considered before because we were only evaluating inverse trig functions and we weren't solving trigonometric equations. So what I'm saying is that going forward, we need to think about these extra solutions that might be popping up that live on the unrestricted portion of the unit circle. So I didn't write in the values here. We're going to do this exact problem on the next slide here, but I wanted to at least motivate this idea for why we are no longer looking at the restricted portion of the unit circle and we're now considering the entire thing. It's because when we're asked to just evaluate, well, that cosine inverse is part of the problem. We are looking at the restricted portion. If we're asked to just solve, we might invoke an inverse cosine, but we are no longer restricted, just like we are no longer restricted when solving x squared equals 4. We'll read this together here. So we're going to look at solving linear trigonometric equations in sine and cosine. So as you might guess, trigonometric equations are equations that involve trigonometric functions. And we may be asked to find solutions over a specified interval. So you can see down here, we're going to find solutions on the interval from 0 to 2 pi. Or we might be asked to find all possible solutions. So here we have, it says final, but it should say find all possible. Find find all possible solutions. If a solution exists at all, so we might find some scenarios, maybe we're talking about tangent, where there's some numbers that aren't in the domain, or secant or cosecant or things like that. But since trigonometric functions are periodic, the solutions are repeated within each period. So I have written here, thus trigonometric equations may have an infinite number of solutions. And if we need to find all possible solutions involving sine and cosine, then we're going to add 2 pi k to the end, where k is an integer. And this is our way to quickly denote k is an integer. This blackboard Z is the symbol for the set of integers. And that symbol E means in. So if I'm writing k in the set of integers, that's what that says, where k is in the set of integers. So, and we'll need to add that to whatever initial solutions we found. So we'll hopefully make sense of this by looking at this example here to see exactly what I'm saying. Oops, I wanted that to still say find. Okay, so we're going to consider this equation that we just did, where we're trying to solve cosine of theta equals 1/2. And I'm still going to do the exact same thing that I did before, which is start by drawing a unit circle. And I'm wondering what angle is going to give me a cosine value of 1/2. So the cosine is positive, and I'm just kind of marking it on my x-axis so I can kind of think backwards to what angle, I know this is one of my common angles, does this correspond to? And we're no longer just restricted to the top half of the unit circle here, but we can look at both the top and the bottom half. So just thinking about what these angles are, this looks like it should be theta equals, what is that, pi over 3. So this is this first angle here. And I know that we could go backwards and get negative pi over 3, but that's not part of our interval that we're looking for here. So we need to go all the way around and get this angle here, which is going to be 5 pi over 3. So this angle, theta, maybe we'll label them theta 1 and theta 2, is going to be 5 pi over 3. Well, maybe I won't label them, so I can just call them both theta. That's fine. I might later on start labeling things theta 1 and theta 2, but let's not do that quite yet unless I absolutely have to. So our theta values in the interval from 0 to 2 pi are pi over 3 and 5 pi over 3. If I want to find all possible solutions, then I need to add, because it's not just that just pi over 3. Maybe let me do this in a different color. It's not just pi over 3, but I could keep going and make a whole other revolution here and come back around. So there's one revolution, or I could make another revolution. There's 2 pi over 3. 2 times 2 pi over... 2 times 2 pi, another revolution, so 4 pi revolution there. So 2 revolutions is what I'm trying to say. But we can make an infinite number of revolutions here. So if I want to get all of them, we will say theta is going to be equal to pi over 3 plus 2 pi, which gives me 1 revolution, but times any integer k. So it could be 2 revolutions, it could be 5 revolutions, or it could be negative 5 revolutions. We could go the other way, but this is accounting for plus and minus. So the integers account for plus and minus whole numbers. And we also have 5 pi over 3 plus 2 pi times k, and then I must say where k is an integer. In general, we're going to be using k to stand for some integer, but it's always important to list it every single time so that in any given problem, if someone is reading it, they know exactly what k means, so that we can get the correct interpretation of the solution here. So there's the first one here. Hopefully that's not too messy, but if we're asked to find solutions in just some interval, then we'll just find those exact solutions. There should be a finite number, or if we're asked to find all possible solutions, here we have infinitely many at all revolutions of pi over 3 and 5 pi over 3. So let's take a look at another example here. We want to consider this equation, 2 sine theta plus the square root of 3 equals 0. So the first thing that we want to do here is just solve for sine theta and see if we can't find some nice relationship here. So if I rewrite this, or maybe the first thing I'll do is just write it over here. Let me subtract the square root of 3 from both sides. So, excuse me, that I'll get 2 sine of theta is equal to negative square root of 3. And then next we'll go ahead and divide both sides by 2. Oops. Divide both sides by 2. So that we get sine of theta is equal to the negative square root of 3 over 2. Okay, that is a common ratio that we should be able to use here. So let me draw my unit circle. maybe draw this one a little bit bigger so as not to get so messy. But I'm looking for a sine value of negative square root of 3 over 2, which is down here-ish. I always just like to visually see where things are so I can get my values in here. But if I'm looking for the sine, that's going to correspond to angles. So not just in our restricted portion of the right half of the unit circle, but we will also get one over here on the left half, and we need to figure out which angles these are now. And so just thinking about the unit circle and these common angles here, this first angle here is going to be 4 pi over 3. So I'm just thinking pi over 3, 2 pi over 3, 3 pi over 3, there's 4 pi over 3, and then this one's going to be 5 pi over 3. So what we're getting here is theta is equal to 4 pi over 3 and 5 pi over 3. And that's just by marking those angles on the unit circle and then using information that we know to figure out what those are. If I want to find, I've got final, I must have copied and pasted, but I want to find all possible solutions here, not final all possible solutions. Now I just want to add 2 pi k to each of these. So we will get 4 pi over 3 plus any revolution in the positive or negative direction. So plus 2 pi k, where k is an integer, and I'll write that next. And then we also have 5 pi over 3 plus 2 pi k, and then we'll write where k is in the set of integers. So there we go. Here is all possible solutions for that equation. Here are just the ones in one revolution from 0 to 2 pi. So next we'll take a look at solving equations involving a single trigonometric function, which is more or less kind of what we just did here. But when we're given equations that involve only one of the 6 trig functions, finding their solutions involves using algebraic techniques and the unit circle. So just like we did on that last problem, we did a little bit of algebra to solve for just that trig function, and then we used the unit circle to figure out the angles that we needed. For problems involving the reciprocal functions, the cosecant, the secant, and the cotangent, we'll write the reciprocal function, so its reciprocal, sine, cosine, and tangent, and solve for the angles using that function. And then an equation involving tangent is slightly different since the period of tangent is pi and not 2 pi. So instead of adding 2 pi k, we'll just add pi k. And the domain of tangent is all real numbers with the exception of odd integer multiples of pi over 2. So we'll need to keep that in mind as well. If those happen to show up as solutions, we'll have something that's undefined there. Okay, so let's see this in action here. We're asked to find solutions for 2 sine squared of theta minus 1 equals 0 on this interval from 0 to 2 pi. So if we can just get sine theta equals some value, hopefully that value is something that we know, some common ratio, and then we can use that to figure out what theta must be. So let me start here by adding 1 to both sides, and we will get 2 sine squared theta equals 1, and then we'll divide both sides by 2, and we will get sine squared theta is equal to 1/2. But we need to get down to just sine theta. I know sine squared theta is something that shows up a lot, but we don't actually know what value that is, or maybe you do because we can find it here. But I would like to take the square root of both sides. And when we take the square root of both sides, remember that we even talked about this earlier, we need to include a plus and minus here. So what I'm getting is that the sine of theta is equal to plus or minus 1 over the square root of 2, which is plus or minus the square root of 2 over 2, which is a common angle, or a common ratio that we know for one of our common angles. So let me draw a unit circle here. And we are looking for where is the sine of theta equal to either plus the square root of 2 over 2, which is, I don't know, somewhere right about there. I know that these are my pi over 4 type angles here, multiples of pi over 4, or negative. So here we're getting both positive and negative. The fact that we got a plus or minus here means that we need to consider both the positive sign, which is the top half of the unit circle, and the negative ratio here, which is the bottom half of the unit circle. So this is going to correspond to either this angle here, which is pi over 4. We're going to be looking at this angle over here, which is going to give us 3 pi over 4. We're going to be looking at this angle down here, which is 5 pi over 4. Or we'll be looking at this angle over here, which is 7 pi. over 4. So there are our 4 angles, and we're only asked for just a single revolution here from 0 to 2 pi, but those are the 4 angles whose sine value are either positive square root of 2 over 2 or negative square root of 2 over 2. So if I wanted to write this explicitly here, I'd say theta is equal to pi over 4, 3 pi over 4, 5 pi over 4, or 7 pi over 4. So there we go. All right, next we will consider this equation, cosecant of theta plus 2 equals 0. First, we're asked to find solutions on the interval from 0 to 4 pi. So that's going to be solutions that include 2 full revolutions around the unit circle. So we'll keep that in mind as we're working here. Okay, so let me first rewrite cosecant in terms of cosine. In terms of sine. Cosecant and sine are the reciprocals of each other. So we will do that here. I'm going to first write, well, maybe first let me subtract 2 from both sides here so that I get cosecant theta equals negative 2. And I'll remember that this is the same as 1 over the sine of theta equals negative 2. And then I can take the reciprocal of both sides, and I'll get sine of theta is equal to negative 1/2. And now I'm looking for some angle whose sine is negative 1/2. So we'll go ahead and draw our unit circle. Negative 1/2 is down here. I'm looking for sine values, angles whose sine values are negative 1/2. So I'm looking at this angle here, and I'm looking at this angle here. So we could call this negative pi over 6, but that is not in our interval here. So we will have to only look in this positive direction. So if I'm looking for what this angle here is, this is going to be theta. Let's see, what is this? This is a pi over 6 plus pi, which is going to be 7 pi over 6. 7 pi over 6. And then if we keep going here, we are going to get to 11 pi over 6. I'm writing them for different thetas because now I'm going to want to complete another revolution here because we are also getting, we need solutions on the interval from 0 to 2 pi. Right now, 0 to 4 pi. Right now we have solutions on 0 to 2 pi. We need to go from 0 to 4 pi. So we need to figure out what this angle is here. So I'm going to just add 2 pi to 7 pi over 6. So another angle is going to be 7 pi over 6 plus 2 pi, which I could write as 12 pi over 6. So this will give me 19 pi over 6. My brain went a little slow there for a second. 19 pi over 6. And then I could also add 2 pi to my 11 pi over 6. We'll keep it green. Theta equals 11 pi over 6. And I want to add 2 pi to that. So we'll add 12 pi. Let me write that a little better. 12 pi over 6, which is 2 pi, to get 23 pi over 6. So here are all 4 of our solutions for 2 revolutions, solving for cosecant of theta plus 2 equals 0. That was our original question here. I know we changed it to sine and solved that way, but this solves our original question here. So now I want to find all possible solutions. We don't need to look at these guys here. I know before we said we're just going to add 2 pi k to our initial solutions, but when we add our 2 pi k on, it will take care of these other 2 here since they are included in more than one revolution. So we're just going to look at the angles that, maybe I'll do this in a different color just since we're on a different question here. If I want all possible solutions, we're going to be looking at theta equals 7 pi over 6 plus 2 pi k. And this includes in it the 19 pi over 6. That would be just plus 2 pi. So we already got that one. And then we also want the 11 pi over 6 plus 2 pi k. And again, we already included, or we are including 23 pi over 6 when we do this, because if k is just equal to 1, then we would get 23 pi over 6 as one of the solutions there. And then we just need to remind our reader and ourselves that k is an integer. And there we go. Here is all possible solutions for theta. All right, moving along here. Next, we're going to take a look at a little bit of a weirder problem, but this says tangent of theta minus pi over 2 equals 1. So we don't just have tangent of theta, but there's this extra bit in there. So let's see how we can deal with this. We're asked to find all possible solutions, and I have a note here that tangent has a period of pi. So instead of adding 2 pi k, we're just going to add pi k to account for all of the periodic solutions here. What I'm going to do first here is, since we have this theta minus pi over 2, that's a little bit strange. What I'm going to say is let's just let alpha equal theta minus pi over 2. And then let's instead solve for tangent of alpha equals 1, because that is a little bit easier for us to solve here. So if I'm thinking about tangent of alpha equals 1, let's draw our unit circle. And there's going to be 2 values that do this for us here. There's going to be this value here at pi over 4. Tangent is positive in the first quadrant, and it's also positive in the third quadrant. So that's not exactly straight, but that's a little bit better. So over here at, what is this? That's pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4. This is 5 pi over 4. Okay, so we've got these 2 values here, but remember that these values are alpha values. These are equal to alpha, and what we're trying to find is not alpha, but what theta is here. So now I'm just going to rewrite. We found that alpha is equal to pi over 4. Let's just start here. But alpha equals theta minus pi over 2. So this is equal to pi over 4 by our previous step. So these say the same thing. They're both equal to pi over 4. Oops. So solving this here is going to give me theta equals 3 pi over 4. And this makes sense. So if I go in and draw this in here, I know we still need to go get the other solution. But if I draw in 3 pi over 4, that is right here. And if I subtract pi over 2 from that, we get back to pi over 4, which is where the tangent value is equal to 1. So yes, 3 pi over 4 totally makes sense as a solution here. And we need to add values of pi to this. So we're going to add pi k to this. We are trying to find all possible solutions here. And then the other solution we're going to get comes from the 5 pi over 4. So maybe I'll do this in a different color. I know that alpha is equal to 5 pi over 4, but what we're trying to solve for is theta, and we have theta minus pi over 2 equals 5 pi over 4. So solving here, we would get theta is equal to 7 pi over 4, and that also makes sense because 7 pi over 4 is over here. My picture's getting a little screwy, but if I go back pi over 2, I would get back to this angle, which I know has a tangent value of 1. So this is making sense here as well. So I will want to add pi k here as well. Yeah, so there we go. Maybe I'll just move some of this work up so it lives in the same area here. I don't know, that seems okay. And now we just want to find the solutions on the interval from 0 to 2 pi. So that's just going to be the 2 explicit ones that we found here. Maybe I'll do this in pink. Just this one or not that one, I'm sorry. That was the alpha that we found, but it's just this angle at 3 pi over 4. So 3 pi over 4. And this other angle here at 7 pi over 4. Those are the only 2 solutions on this interval from 0 to 2 pi. So we did that one a little bit backwards. We found all the solutions first, and then we just figured out which ones were on our interval there. So there we go, a bit of a different looking problem where we're not solving, or the argument has a bit more going on than just the angle that we're trying to solve for. All right, taking a look at what we have next here. So next we're going to look at solving some trig equations using a calculator. You might imagine that as you're solving some of these problems, it's not going to work out super nice to where we get one of these common ratios and you'll have to use your calculator So whatever near naughty function can be solved exactly using only the unit circle. When we must solve an equation involving an angle other than one of the special angles, we will need to use the inverse functions on a calculator. Since the calculator will only return angles in the restricted domain, it's important to find any angles outside of the restricted domain. So we'll need to do a little bit extra thinking. The calculator will do half the work for us, and then we'll need to do the other half ourselves. So what we're given here is the secant of theta equals -4, and theta is in terms of radians. So that'll help us when we get our calculator out. We don't need to make sure that we're in radians. I'm going to rewrite this as 1 over the cosine of theta equals -4. So that I'm just getting this in terms of cosine, since that is something that we're a little bit more comfortable with. So taking the reciprocal of both sides will give us cosine of theta equals -1/4. So since that is not a typical ratio for us here, so just to kind of draw this in here, cosine of -1/4 is here, and there's going to be two spots, or two angles rather, where this is true. There's an angle here, and there's an angle here, but these are not common ones, so we'll need to use our calculator to figure out what these values are. So what I'm going to do is look at cosine inverse of -1/4 equals theta. Now, when I put this in my calculator, since I have a cosine inverse, it's only going to give me this top angle here. It's only going to give me the one that lives on the top half of the unit circle. Then we'll have to go figure out what the other one is by using some reference angles. So let's switch over to the calculator here. And we are looking for the cosine inverse of -1/4. So let me put in 0.25 negative. So that is -1/4. Just in decimal form, and I'm going to look at the cosine inverse, so I'm just pressing the cosine inverse button, and that gives me about 1.8235, so rounding to this decimal place here. Okay, so let's go back to our screen. So here we're getting that theta is about, and we'll call this actually theta 1, since we're looking at a specific theta here. I'm going to want to reference these different theta values. So we'll say that theta 1 is about, what did I just say, 1.8235. So this angle here, this theta 1, we're saying that's about 1.8235. But we know that there's another angle here. We need to figure out what theta 2 is. So there's this other angle here, which we'll call theta 2. Just label it kind of off here, off to the side. Now note that this, well, let's look at this reference angle. Maybe I should have made things a little bit bigger. Let's see if I can't make it a little bigger. Whoa, a little too big. So if I'm looking at just this reference angle, so we'll do this in blue here, just this reference angle right here in blue, notice that the full distance from here to here is pi, so that's pi, and then I want to subtract off our angle, which is theta 1. And this will give us a value of about 1.3181. So I'm just getting some approximations here. And now this angle that we actually want, this theta 2 angle here, is going to be 180 degrees plus our reference angle, or plus our reference angle of 1.3181, etc. So this angle here, theta 2, is going to be this distance of pi plus our reference angle, which we just found is so I should write approximately here as well. Approximately pi plus 1.3181. So here we're getting that theta 2 is approximately, adding those together, and we get 4.4597. And then just looking back, we were asked to not find any sort of restricted or solutions over some sort of restricted domain, but to find, it doesn't say, but we'll assume this means all possible solutions. So to this, we need to add plus 2 pi k, and we'll add plus 2 pi k, where k is in the integers. So here we go, kind of crammed into the bottom a little bit here, but we've got all of our solutions. So the one here on the left in yellow, we got from using the cosine inverse button on our calculator, and then we needed to use the unit circle and the geometry of the situation to figure out where this other angle was on the bottom half of the unit circle, where we don't restrict our domain. So there we go. We've got both of our angles here. We'll use similar techniques going forward to do the same thing. All right, next we're going to look at solving trig equations in quadratic form. So if we notice that a trig equation is written in a quadratic form, it can sometimes be helpful to make a variable substitution to just visually make the problem easier to solve. It's not required to do this, but I do think that it can make things nice. So here we're going to let some variable, and pick your poison, but I usually use u to make substitutions. We're going to let u be equal to sine of theta. And then if I rewrite what we have here, and maybe I should have said this first, but I'm just noticing that this looks very much like something in quadratic form. I have a term that's squared, I have the same term that's not being squared, and then that term disappears. So that is what I mean by quadratic form here. So I could rewrite this now as 2u squared minus 5u plus 3 equals 0. And this just visually tends to be a little bit easier to solve. So like I said, you don't need to make the substitution, but it can be helpful, at least when you're starting out, or definitely when you're starting out. If I try and factor this guy here, I'm going to get 2u and u, and then I think that I want minus 3 and plus 1. Just thinking about this quickly, that'll give me 2u squared plus, I'm sorry, I'm on a minus 1 at the end here, don't I? Minus 1. This will give me the plus 3 at the end that I want, minus 5u in the middle. Okay, now I've got what I want. I had my signs backwards for a second. Let me substitute back now, because what this actually says is that we have well, actually we can just solve. Let's solve, and then we can go from there. What this is saying is that 2u minus 3 equals 0, or u minus 1 equals 0. So we get that u is equal to 3/2, or u is equal to 1. But we're not trying to solve for u, we're trying to solve for theta. So we've made the substitution, now we're just going to substitute back. So we're actually looking at the sine of theta is equal to 3/2, or the sine of theta is equal to 1. And now we can look at solving each one of these individually. So we can draw a unit circle. You might be noticing something weird about that first one, but let's make sense of that here as soon as the circle completes. There we go. So for the first one, we're looking for some angle that'll give us a sine value of 3/2. Well, 3/2 is like up here. So we're never going to get a sine value of 3/2. 3/2 is not in the interval from -1 to 1. So there is no solution here. So we can throw that one out as being extraneous or something, but there's no solution to that half. But I do know that there is an angle that'll give me a sine value of 1, and that is this angle here at theta equals pi over 2. And that is the only solution where the sine is equal to 1. Down here we get -1. So just one solution here, and we were asked to just find it on the interval from 0 to 2 pi, so we don't need to add 2 pi k here to account for all solutions. So there we go. We did a quadratic substitution to solve here. This one worked out nice because it factored, but we might see some examples where they don't factor. So let's take a look at that next. So here we want to find solutions again on the interval from 0 to 2 pi. So we can do the same thing that we did before. We can let u equal the cosine of theta. I'm just noticing I've got a term squared, I've got a term not squared, and then that term isn't there. So this is in quadratic form. So I can rewrite this now as u squared plus 3u minus 1 equals 0. And we can spend some time to try and factor this, but I'll just tell you right now that it does not factor. So we're going to need to use the quadratic equation. So just plugging that in, we're solving for u. Remember, the quadratic equation solves for the variable here. We're going to get u is equal to -b plus or minus the square root of b squared minus 4 times a times c all over 2. And then simplifying here, we're going to get -3 plus or minus the square root of 13 over 2. Okay, again, we're not trying to solve for u, we're trying to solve for theta, and we made the substitution. So what we actually have here is that the cosine of theta equals -3 plus or minus the square root of 13 all over 2. And now let me make a note here. I'll do this in pink. Whoops. I'll say note that -3 minus the square root of 13 over 2 is not in the interval. Write that a little better. Is not in the interval from -1 to 1. So just like before, we can throw that solution out as being extraneous, and we can just look at the positive version here. So in my next step, we are looking at cosine inverse of just -3 plus the square root of 13 over 2 is equal to some angle theta here. So again, we threw out the negative version because this does not live in the domain of cosine inverse. Or I'm sorry, the negative version doesn't live in the domain of cosine inverse. And now we need to do a little bit of work. So we're going to go plug this into a calculator here. In fact, I'll just tell you that what we get here is that theta is about 1.26. Pi over 2 is a little bit more. That's 1.5 something, since pi is 3 point something if I divide that by 2. So what I'm just saying here is that this angle must live in the first quadrant. So I'm just trying to think about the situation here, since I used a calculator to find this. So maybe I'll just write that in here. Use calculator. But this is only going to give us the solution that lives in the top half of the unit circle. So this angle is like, I don't know, somewhere around here, I think. But like I said, our calculator is only going to give us the solution, the angle that terminates in the top half of the unit circle. But there's another angle that lives down here in the bottom half of the unit circle, and we need to find that one as well. So this angle here, this top angle, this theta 1 we can call it, is our about 1.26. That's also our reference angle here. So if I want to find going backwards, we could say that that's negative 1.26, but that's not in our interval from 0 to 2 pi. So what we need to do is instead think about making one full trip around to 2 pi. So if I'm finding theta 2, we'll think about doing 2 pi, and then we'll subtract off just the reference angle, which is the 1.26. Whoops, 26. So our theta 2 here is going to be about, putting that into a calculator, we get about 5.02. So there are our approximate solutions to this one, theta 1 and theta 2. We're just calling both theta if you want. I just wanted to label them differently so that we could talk about them distinctly, since we are subtracting one from the other. But there we go. There is our two solutions. So again, we need to make sure that if we're using a calculator to solve, that we are using some reference angles to figure out the other angle that lives on the unrestricted part of the domain. All right, next we are going to solve some trig equations using the fundamental identities. So if we take a look here, I've got cosine of some value times cosine of some other value plus sine of some value times sine of some other value is equal to one of these common ratios. So what I'm noticing here is that we have something of the form cosine alpha cosine beta plus sine alpha sine beta, which is cosine of alpha minus beta. That is that identity. So we're just going to apply that over here. What I'm noticing is that alpha is equal to x and beta is equal to 2x. So if I just use my identity here, we're getting cosine of x minus 2x is equal to square root of 3 over 2, which is going to give me cosine of negative x equals square root of 3 over 2. If I use the even identity here, I can think about just ignoring that x really. What is equal to the cosine of negative x is just the cosine of x. These are equivalent to each other. is equal to square root of 3 over 2. And now I have something more standard that I can solve here. So let me get my unit circle in. If you have these values memorized, then you can just use them. I always need to just double check on my unit circle. Cosine of 3 pi over 2 is way over here, so I'm going to be looking at this very shallow angle, which is pi over 6. And this other very shallow angle over here, which I could call negative pi over 6, but that's not on our interval, so I need to go all the way around here and think about this angle as being 11 pi over 6. So there we go. There are our two solutions here. For x, we're calling it, which is pi over 6 and 11 pi over 6. So there we go, using one of our fundamental trig identities to solve this guy here. All right, let's take a look at using a different fundamental trig identity to look at this one. So what I'm noticing here, again, we're asked to find solutions on the interval from 0 to 2 pi, so we don't need to find all solutions. But I'm noticing that there's a cosine and there's a sine squared, and I have two different trig functions here. If I just had a single trig function, then I might have a better chance of solving this. So that's what I'm going to do. I'm going to use the identity that sine squared of theta is equal to 1 minus the cosine squared of theta. And I'm using that because that will get me cosines everywhere here. I mean, we'll just be in terms of cosine. So let's make that substitution. We'll have 3 cosine theta plus 3 is equal to 2 times 1 minus cosine squared theta. Then we will distribute this 2 here, and we'll get 3 cosine theta plus 3 is equal to 2 minus 2 cosine squared theta. Now this is starting to look like it may be in quadratic form, so let's just try and get everything on one side here. So if I add 2 cosine squared theta to both sides, plus 2 cosine squared theta, and I subtract 2 from both sides, then those will cancel, and then I'll be left with 2 cosine squared theta plus 3 cosine theta minus plus 1 equals 0. So yes, definitely in quadratic form now. We could go and use that u substitution, but I'm just going to factor this how it's written here. We're going to get 2 cosine theta plus 1 times cosine theta plus 1. That's the only way I can multiply that out to get what we got above. So yeah, again, you can make a u substitution or whatever sort of substitution and solve here. But that's what I'm getting. So this tells me that 2 cosine theta plus 1 equals 0, or cosine theta plus 1 equals 0. And if I solve for each one of those individually, just block that off there, we're going to get that cosine of theta equals negative 1/2, or cosine theta equals negative 1. So now I have a couple different solutions to solve for, different couple areas to solve for here. So just thinking about this unit circle, I'm looking for cosine being negative 1/2. Negative 1/2 is here, so that's going to correspond to these angles. So this is 2 pi over 3, and this angle here is going to be 4 pi over 3. So that is what is, those are the solutions from this half of the product here. And we'll get the other solution from cosine, whoops, that's not what I wanted. From cosine being equal to negative 1, and this one's a little easier to find. Cosine of negative 1 is there, which is just at pi. So our solutions here on the interval from 0 to 2 pi are going to be 2 pi over 3, pi, and 4 pi over 3. So there we go. Here, being able to factor, split that into a couple of terms, and then we just solve each term individually to get all of our solutions. All right, next we're going to look at solving multiple angle trigonometric equations. So here we can see we have a double angle. So we're going to need to think about that as we look for all of our solutions here, and we're on the interval from 0 to 2 pi. So we're not finding all of them, but we're finding one specifically on this interval, which actually means there is a little bit more work to do. Okay, so what we're going to do here is we're going to make a substitution, and we're going to let alpha be equal to 2x. Just so I could rewrite this as cosine of alpha equals 1/2. All right, now that we have cosine of alpha equals 1/2, we can just go ahead and put in our unit circle so we can figure out what this value is. So you either know it already or you're like me and just need to figure out what it is. So we're looking at 1/2. So if I'm looking up here, down here, we're going to be looking at this angle, which is pi over 3, or this angle down here, which is going to be pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3, 5 pi over 3. I could have gone back the other way and subtract. Okay, yeah, this all makes sense to me here. Okay, so here are my two alphas. So these are alpha, but I'm not interested in alpha. I'm interested in x. So I've got now that alpha is equal to pi over 3, or alpha is equal to 5 pi over 3. But what I want to solve for is x. So let me substitute back and write this as 2x equals pi over 3, or 2x equals 5 pi over 3. And if I divide both sides by 2, I get x is equal to pi over 6, or x is equal to 5 pi over 6. So there's a couple of angles, and of course, pi over 6 lives over here, and so it makes sense that when you double that, you end up at pi over 3. And then if we're at 5 pi over 6, which is over here, it makes sense that when you double that, you end up at 5 pi over 3. So 5 pi over 6 is about, around there. Okay, so those are what we're solving for x, but notice that this might not give us everything in this full interval here. So we're going to need to think a little bit more. So remember that I could also add not just pi, but 2 pi. I could add 2 pi to each one of these and get another solution. So that's what I'm going to do here, and it might not be clear that's what we want to do yet, but we will actually find some other solutions by doing this. Maybe let's switch to blue, and let me maybe move my unit circle here out of the way. So what I'm saying is that, it is also true that 2x equals pi over 3. I might want to add 2 pi to that as well. And it's also true that 2x is equal to 5 pi over 3, but I could add 2 pi to that as well and get another angle. And we'll see that when I solve for x, we'll still get some angle, some solution that is in our interval from 0 to 2 pi. So if I do a little bit of algebra here, I'll get that 2x is equal to, if I do a common denominator, I already have 6 pi over 3. So adding those together, we should get 7 pi over 3. And we should also get that 2x is equal to 11 pi over 3. And then if I solve for x here, I'm going to get that x is equal to 7 pi over 6, and x is equal to 11 pi over 6. And both of those angles are on this interval from 0 to 2 pi. So let's check another revolution, because it could be that another revolution, once we solve, gives us angles on this interval from 0 to 2 pi. So let me not erase that, but maybe move it. Just never like erasing. I'll just put this guy over here. Oops. And we'll just change color to make sure that things are clear here. But it could also be true that 2x is equal to pi over 3, and then we could add 2 revolutions to that, which is 4 pi. And 2x is equal to 5 pi over 3 plus 4 pi. And then doing a little bit of arithmetic here will give us that 2x is equal to 13 pi over 3, just cutting to the chase there, getting a common denominator and adding the numerators, or 2x is equal to 17 pi over 3. Yeah, 17 pi over 3, and then solving for x, we'll get that x is equal to 13 pi over 6, and x is equal to 17 pi over 6. And those angles are also on the interval from 0 to 2 pi. So if I go through and just erase not erase, but box everything we have, we've got pi over 6, we've got 5 pi over 6. We added another revolution to our initial alpha values, and then divided by 2 again, and we got more solutions at 7 pi over 6 and 11 pi over 6. Then we added another revolution, so now we're 2 revolutions around, and then dividing by 2, we found more solutions at 13 pi over 6 and 17 pi over 6. Now, if we went at this point and added not 4 pi, but 6 pi, we would see that we would end up outside of the interval that we're interested in. So I will just say, in general, I'll just use this little space at the bottom here. In general, when solving for sine of nx or cosine of nx, we must go around the unit circle n times. So notice that since we had a 2 pi here, we finished these by going around the unit circle 4 pi, which is 2 revolutions. So that's what we're saying here. We must go around the unit circle here. It was 2 times, which is equivalent to 4 pi. That's why we could stop and we didn't need to add 6 pi over here because that would have been another revolution, being 3 revolutions, which is more than the 2 that we had. So if you ever want to know how many revolutions to check, it is very much related to the coefficient in the argument here, so the 2x here. So there we go. We end up with 6 solutions here, 1, 2, 3, 4, 5, 6, by just checking multiple revolutions around the unit circle. So there we go. All right, from there it is time to practice. So please let me know if you have any questions. Good luck with the homework. I'm always here to help if you do have questions, and I will see you in our next video.